Hello friends, so welcome to the second lecture on the iterative methods for solving linear systems. So in the previous lecture we have learned two schemes, one is Jacobi and another one is Gauss-Seidel for solving the linear systems. It has been seen that Gauss-Seidel method converges towards the exact solution in less iterations when compared to the Jacobi scheme. There are many problems where these two schemes do not converge at all. In this lecture, we will learn a more generalized scheme that is called successive over relaxation. Finally, in the last phase of this lecture, we will discuss the conditions under which these iterative schemes means Jacobi, Gauss-Seidel and successive over relaxation converges. So, as I told you in the previous lecture, these schemes are called non-stationary iterative methods, means these are of the form x k plus 1 equals to iteration matrix P times x k plus q. So, these are the stationary method. So, now consider Ax equals to b. Write A is the sum of three matrices L, D and U times x into B. Now, what you do? You write D plus omega, omega is where some scalar times L plus 1 minus omega L plus U into x equals to b. So, if you observe this, this is just omega L plus L minus omega L. So, this is just this L only. Now, what you do? You write your iterations like this: d plus omega L x at k plus 1 iteration equals to minus 1 minus omega L plus U x at k iteration plus b. Now, if in this equation, if I take omega equals to 0, then what will happen? So, it will become d x k plus 1 minus 1 L plus u x k plus b. So, this becomes Jacobi's scheme. If I take omega equals to 1, then it becomes Gauss-Seidel scheme. For omega equals to 0.5, this is somewhere between Gauss-Seidel and Jacobi. For omega greater than 1, we have a method beyond Gauss-Seidel. So, in this way we can say we are having some sense of over relaxation in this case, and for certain problem it turns out to be highly effective method. Now, consider an iterative scheme for a n by n linear system x equals to b as d plus omega L at x k plus 1 iteration equals to minus 1 minus omega L plus u x at k iteration plus b. Now, it is possible that is the same thing which I have discussed in the last slide. So, it is possible to recast above scheme in such a way that the matrices on the left and right hand sides are lower and upper triangular respectively. So, it is lower and it is upper. This allows us to use the concept of successive displacement, and over relaxation can be implemented in a manner similar to the Gauss-Seidel method, with new variables values overwriting old ones as soon as they become available. This type of iterative method is known as successive over relaxation, or in short SOR. So, the iterative process of SOR method is the same as the other stationary methods, that xk plus 1 equals to the iteration matrix P times x at k iteration plus the column vector q, where omega is between 0 to 2, where omega is called a relaxation parameter. For omega greater than 1 we say it over relaxation, for omega less than 1 we say it under relaxation. One more thing, that how to compute the optimal value, because omega will be between 0 to 2. So, what will be the optimal value for a given problem, so that the scheme converges faster. So, that optimal value of the omega for the SOR scheme can be given by this one. So, omega optimal will be 2 upon mu square multiplied with 1 minus square root of 1 minus mu square, where mu is the spectral radius of the Jacobi iteration matrix, and if you can recall, Jacobi iteration matrix is minus D inverse into L plus U. So, calculate all the eigenvalues of this, and the eigenvalue bigger in the magnitude will be the value of mu, that is the spectral radius of this iteration matrix P. And once you are having mu, you can calculate the optimal value of omega using this particular formula. Once you are having omega, then you can put the value of omega here, and you can calculate the iteration matrix P as well as column vector Q, and you can write your iteration equation, iterative equations of SOR method. So, for this let us take this particular example. So, consider the linear system 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2. So, this is the coefficient matrix A multiplied with column vector of unknown variable x1 x2 x3 equals to right hand side vector B as 7 1 1. Develop the iterative scheme using the successive or relaxation method. Also perform 3 iterations of this method by taking an initial solution as 0 0 0. So, x1 is 0, x2 is 0 and x3 is 0. So, if we see, the coefficient matrix A can be written in terms of a lower triangular matrix L, a diagonal matrix D and an upper triangular matrix U. So, for this matrix A, L will be this, D will be like this and U will become this matrix. Now, as we know, the iteration matrix for successive over relaxation is given by this particular scheme. So, if I calculate here, the iteration matrix in terms of omega comes out to be in this form. So, first element is 1 minus omega, second is omega by 2, third one is 0. Then in the second of first element is omega into 1 minus omega by 2, second element is 1 minus omega plus omega square upon 4, and the third element in the second row is omega by 2. Then in third row, first element is omega square into 1 minus omega upon 4, omega 1 minus omega upon 2 plus omega cube upon 8, and the third element is 1 minus omega plus omega square upon 4. So, this is the matrix which is the iteration matrix for successive over relaxation method, and the column vector Q comes out in this form. So, now what we need to do? We need to calculate the optimal value of omega, and we have to substitute that value here to get the iteration matrix P in the form, so that we can perform the iterations. So, as I told you, the optimal value of the omega will be a function of mu, where mu is the spectral radius of the Jacobi iteration matrix. So, if I calculate the Jacobi iteration matrix for this problem, it comes out to be minus D inverse into L plus U, and in this way. The eigenvalue of this matrix are 0, plus 1 upon root 2 and minus 1 upon root 2. So, it gives the spectral radius mu as 1 upon root 2, and hence the optimal factor for SOR scheme is omega optimal is 2 upon mu square 1 minus square root 1 minus mu square by using this formula, and it comes out to be 1.171573. After substituting this value of omega into this iteration matrix and the column vector q, we obtained this matrix P as the iteration matrix and this column vector as the q. Now, take x1, x2, x3 as 0 in the initial solution. So, in the first iteration we obtained x1 as 4.1006, x2 as 2.9879 and x3 as 2.3361. These are the values of x1, x2 and x3 in the second iteration, and in the third iteration we obtained x1 as 5.8283, x2 as 4.8731 and x3 as 2.9606. So, these are the 3 iterations of SOR method. So, this is how we can implement the successive over relaxation scheme. First, write down the iteration matrix in terms of omega from the formula of iteration matrix as well as the column vector q. Find out the optimal value of omega, substitute there, and from there you will get the iterative equations for the successive over relaxation method. After this implementation, we will talk about the convergence analysis for all these iterative methods. So, we are talking about convergence analysis. Of the stationary iterative schemes. For solving linear systems. So, consider a linear system Ax equals to b, where A is a n by n matrix, and let the exact solution of this system becomes x equals to s. So, if we apply stationary iterative scheme on it, then we are having the scheme of the form x at k plus 1 iteration is p at x at k iteration plus q, where p is the iteration matrix and q is column vector. Now, since s is the exact solution, so what we are having, s equals to p times s plus q, because s is the exact solution, and once you obtain the exact solution, then whatever iteration you perform, you will get the same solution. That we have seen in case of the example of Jacobi as well as Gauss Seidel in the previous lecture, where in case of Jacobi in 45th and 46th iterations you were getting the same solution, and in case of Gauss Seidel you were getting the same solution in 9th and 10th iteration. So, now let us say equation 1 and this is my equation 2. Now, if we subtract equation 2 from equation 1, we have x k plus 1 minus s equals to p x k minus s. Okay. Define E I equals to x I minus s as the error in the ith iteration. Then what we are having? We can write this equation as E, that is error in k plus 1 iteration, equals to p times error in kth iteration, or this I can write norm of error, because this error will be a vector for different variables x 1, x 2, x 3 up to x n. This can be written as norm of the error vector in kth iteration. So, what we are having? We are having the error vector in k plus 1 iteration equals to the norm of error vector p times error vector in kth iteration, and this can be written as norm of p into norm of E k. So, what we are having? E k plus 1 less than equals to p, that is norm of p into norm of error vector in kth iteration. Now, if this norm of p becomes less than 1, then what we are having? The error in k plus 1 iteration is less than error in kth iteration. Now, this is quite important. This tells us that whatever error you are having in first iteration, in the second iteration you will be having the less error. Whatever error you are having in second iteration, in the third iteration you will be having the less error, means you are going towards the exact solution, and this is happening due to this condition. So, based on this, what we can say, that we can write the sufficient condition for the convergence of an iterative scheme, and that sufficient condition becomes that even if our initial approximation has a large error, the first iteration is certain to reduce that error, the second is certain to reduce it further, because in each iteration you are having less and less error, and so on. It follows that the error in kth iteration will be 0 when k is tending to infinity, which implies that the sequence of approximation will move towards will tend to exact solution as k tending to infinity, because this error is tending to 0. Hence, a sufficient condition for the convergence of iterative equation can be stated as, if the norm of matrix P is less than 1, then the iterative scheme x k plus 1 equals to p x k plus q is convergent for any initial solution, because whatever large error you are having initially, it will reduce in each subsequent iteration. Here one important remark I would like to mention, because there are different types of matrix norms. So, if we choose a particular matrix norm, say the infinity norm, and if we find that this infinity norm for the iteration matrix P is greater than 1, this does not indicate that the iterative scheme will fail to converge, because it is a sufficient condition, not necessary first of all. And moreover, there may be some other matrix norm such as 1 norm or Frobenius norm that is strictly less than 1, in which case convergence is still guaranteed. So, there should be one norm is less than 1 that will do our job, then guaranteed we can say that the iterative scheme will be convergent for any initial solution. So, in any case the condition the norm of iteration matrix P is less than 1 is only a sufficient condition for a convergence, not a necessary one. Now, we will write the necessary and sufficient condition. The iterative scheme x k plus 1 equals to P of x k plus q for solving a linear system A x equals to b is convergent for any initial solution if and only if every eigenvalue of P satisfy lambda is less than 1, means every eigenvalue of P is less than 1, or in other way we can say it, the spectral radius of P is less than 1. So, this is the necessary as well as sufficient condition for the convergence, means if scheme is convergent, then the every eigenvalue of P will be less than 1, and if every eigenvalue of P is less than 1, then scheme will be certainly convergent. These conditions I have spoken, they are on the iteration matrix B. Can we say some condition on the coefficient matrix A, because the coefficient matrix A is directly available to us from the problem. P we need to calculate. So, here I am telling one more condition which can be implemented on the coefficient matrix A, and that sometimes a guarantee of convergence can be established by direct inspection of the coefficient matrix A, that is as I told you without needing to compute the iteration matrix P. In particular, if A has the diagonally dominant property, then the Jacobi and Gauss-Seidel methods are both certain to converge, and a matrix is said to be diagonally dominated if in each row the absolute value of the entry on the diagonal is greater than the sum of the absolute values of the other entries. So, consider this particular example. In this example, comments about the convergence of Jacobi iterative method for the following matrix. So, here this is my coefficient matrix. So, if you see the coefficient matrix here, the diagonal entry in first row is 5 and sum of the absolute value of the other entries are 3. So, 5 is greater than 3, here 8 is greater than 2 plus 1 and here 4 is greater than 2 plus 0. So, it is a diagonally dominant matrix, strictly diagonally dominant, and hence the scheme will converge. Moreover, if you want to check with the iteration matrix, if I calculate iteration matrix in case of Jacobi method, it comes out to be in this way, and if I find out the norm of this, the infinity norm is 0.10 and one norm is 0.75, both are less than 1, and hence these are the sufficient, these are guaranteed the scheme will converge, Jacobi scheme will converge. Comments about the convergence of Jacobi iterative method for the following matrix. Now, this is an interesting example. Why I am saying interesting? Let me describe it. So, here I am having a system Ax equals to b, where the matrix A is minus 2, 0, 4, 2, minus 8, 1 and 5, minus 1, 3. If you see this matrix, in first row the diagonal entry which is 2, it is less than 0 plus 4. So, this matrix is not diagonally dominant in this form. However, if I write the equations, the first equation becomes minus 2x1 plus 4x3 equals to b1. The second equation is 2x1 minus 8x2 plus x3 equals to b2, and 5x1 minus x3 plus 3x3 equals to b3. Now, what you do? You just interchange first and third equations. So, if I interchange it, my system will become 5x1 minus x3 plus 3x3 equals to b3. The second equation will be remain like the earlier, and this one 4x2 4x3 equals to b1. Now, these two systems are same, they will be having the same solution, just I have interchanged the order of equations. Now, if you see the coefficient matrix of this system, it will become 5 minus 1 3, 2 minus 8 1, minus 2 0 4. So, what will happen if I take this coefficient matrix, it is diagonally dominant, because in each row diagonal vector, diagonal element is having the bigger value when compared to the sum of the absolute value of other one in terms of absolute value. And what you do, apply the Jacobi scheme on this matrix instead of this one, because you will get the same solution only and your scheme will be guaranteedly converge. Take one more example. Let A becomes 4 2 minus 2 0 4 2 and 1 0 4. Here matrix is not strictly diagonally dominant, because if you see the first row 4 equals to 2 plus minus 2. So, which are same. So, what we are having here, we cannot comment, even though we change the order of the equations, it will not, it will become more worst. So, we cannot comment anything after seeing the coefficient matrix. So, if we talk about Jacobi method, and let me calculate the iteration matrix for Jacobi method. So, it will become minus d inverse into L plus u, and it comes out to be 0 minus 0.5 0.5 0 0 minus 0.5 minus 0.25 0 0. If I calculate this norm, it comes out to be 1, and if I calculate this norm, this is also 1. So, what will happen? Not diagonally dominant, this norm is 1, this norm is 1. So, what is the other choice left with us? Calculate this also, because based on this I cannot say whatever information I have calculated, I cannot say anything about the convergence. So, calculate Frobenius norm, and fortunately it comes out to be 0.901, which is less than 1, and hence since one of the norm is less than 1, then convergence is guaranteed. It satisfies the criteria of sufficient condition. In this lecture, we have learned about the successive over relaxation scheme, then we have seen the convergence conditions for different stationary schemes. In the next lecture we will talk about non-stationary iterative scheme. So, thank you very much.